Testing. Alright. First, where's this? Spain. Fuerteventura. It's an island. Canary Island. An archipelago. Okay. Looks nice. Anyway, we're back to this. Okay, where are we now? Let me look at the example. So let's do this. We would keep track of profit so far, right? So like this is actually DP now. So we would do so with some example like if we sort the 35, 17 is a profit, and difficulty is 47. Profit is this, right? 52, profit is 1. 56, 68. Profit is 67. 6, 3. So we want it to become okay, so this is actually a list now. Let me check if YouTube is correct category. Yeah. Okay. So if it is difficulty 35, then we want it to become 35, 17, 17. Right. So 47, 81, then it could be 81. Right. If it is 52, 1, then it would be 81. Right. So if we found out that it is 68, 67, will still be 81. And if we found that it's 86 and 86, difficulty is 36, then profit would be 81, right? So 81, right? So 3. So we would maintain a left pointer. We call this profit so far, right? So we would do profit equal, and profit here will be greater than 1, right? So -1. So if profit equal -1, then if p dot profit gonna be equal to the p of -1. Okay. So the outcome of this is we want dp to append profit. So max profit so far, let's call that max profit so far, right? So we do max profit so far, and max profit so far, right? Okay, so it's gonna be equal to dp. That's the one. Right, so first we got this -1, we got this, or right, so the profit for 86 would be this out of this way. So we always swap, right? If it's as long as it's less than this, then we found them, right? If our max profit so far is less than the current, right? So say we want to look for 92, so it would find 86, right? And then 86, the maximum profit is actually 81. If we found 85, then it would found 68 here, and the profit should be 81, right? So basically if the max profit so far is less than the current profit, this is like, let's do 0, 1, right? Let's just do 1, right? To signify that we didn't pick the last one. Okay, so we always append this, and so first when we do this, it's gonna be 17. When we do this, because 17 is less than that, and it's gonna be this, right? and the third one is, and continue on to that, right? So that means once we found this, all of this can be replaced with, so once we find the DP, right? Okay, as long as it's all this can become, right, all of this can become, the profits will be plus equal to difficulty profit minus 1, right? DP minus 1, right? So we have any number and we found it in here in the max profit that we just put it here, right? So I think this would be better. Let's run them. Let's see. Okay, so that still pass. And let's see our runtime, because now we have basically we do a n log n here, and this is an on here. So and here's n log n, right? So basic, wait, this is om because it's this worker, right? om log n, right? So so I think that we did this will give us a runtime of O of m, which is number worker, and log n because we log for this, we find this and we found the max right away, and this is om right here. So this is o n, okay? So it will be that. Submit. See. Okay, what is our previous runtime? We beat 36%. That's good enough for me. We stole the max profit so far by the difficulty, so that once we binary search a value, we got the max profit right away instead of previously search for that. Okay. This, what is it? What is the improvement here compared to previously? That was 7, 8, 10 divided by 95. That was like 80% improvement. Not bad, not bad. So complexity is O of n log n, right? So let's confirm that's the case here. Yep, perfect. Because m is the number of worker, and once we can binary search, I kind of cheated with the bisect, right? But you can easily implement that. But I think we did implement bisect left and bisect right in a previous session, right? We did it here, right? In the, what was that? Substack 7, right? So if I search for bisect, yeah, we did this in cow0 request server, right? Where we just binary search for stuff left and right. So left mean the leftmost duplicate number if found, Right mean the right mode duplicate number if found. Otherwise negative one. So we did that. So this is Substack 8. We will commit them to VS Code. Let's see. Okay. So now um, commit to VS Code. Okay. So this is our implementation. Okay, so let's move this into solution 1, right? Solution 1. Self difficulty profit. So we put this to this. What happened? Oh, whatever. Okay, so now we want to return self.solution 2, right? Difficulty profit. Okay, solution 2 is we will click this. Put this here. Oh, we did have that. Okay. So the solution has runtime of mlogin. This is 80% increase. This 95. We beat a 36. 36. And the memories is a little bit more, right? Because now we have a third element here. I'm sure we can cut this down and remove this cache maybe. Oh, hit this. This one beat only 8%. Okay, so making sure the things still work. On. Oh, yeah. Yep. Hello. Yeah. Let a man. Okay. So that's fine. Yeah. Okay. Should we do an easy one and then switch over to the Kafka stuff? Okay, let's do a small one. Okay. Given an array of integer, check if that exists to indices. Okay, so we would loop through this. We build a frequency, right? 10 with index. 10 is index 0, whatever, right? And after that, um, we loop through them, right? And we check if, for example, if it is 10 is indeed the number, then we need 20, right? Then we check 20 in, right? We also need to check if the index the same, right? It shouldn't be the same, right? Okay, let's do that. So that gonna be on, right? I guess so. Okay. Frequency. This is a map for I up an element n in R, right? In enumerate up R. We say that if is the number unique, because then if we have like duplicate, right? And even if we have duplicate, then we still need to check if, okay, let's do that. So if n is not in frequency, then frequency up n colon empty, and then frequency up n append I, right? Then we loop to for n in R, right? And we say if out of this we return false, right? So we would check if 2 multiplied by n is in this frequency, and also we need to check if the index are the same, right? So basically this number and this okay, so for example, if we have like the case that work, oh sorry, yes, that was different style of comment. So like for example, we have 10 map to 1, right? And let's say we have 20, right? Is it possible that they are, it's not possible, right? So let's say we have duplicate, right? 10 1 3, right? And the 20 would never be the same, right? I think. Right, so even if because the number and the duplicate, right, is gonna be in different bucket, right, if it exists. And if it's in different bucket, it's just not gonna share the same index, right? So let's just do this and return true, right? Try it out. Okay, submit. Does it work? Is there any edge cases? Oh, they have negative. Okay. Oh, 0. Okay, so basically we have, okay, 0 to multiply by 0. Okay, so if 0 is the 1. Okay, so you want false. So in this case, we forgot that the number 0 is special here. So, okay, so what they say? They do not mention anything about like absolute number or whatever, right? Right, so the thing we have to do is, if it's not equal to n, and to multiply n in this, right? So this should guard again that case, right? Yeah, forgot about 0. Oh, so this is 0 special case, right? So this expects true. So we still have to check the index here, right? So, and okay, so if it is, so this would fail this, right? So should we just specialize special case the 0 then, right? So here, if we, so this was, for example, we would have, yeah, our map would have 0 from 0 to 1. Yeah. So the case actually, if it is, even if it is in, right, we have to check if, and the length of the 2n actually, right, have to do to be greater than 2, right? Greater than 1, right? Let's just also use this test case, run. What is this? Oh, length of frequency of this. Because we want to, because in the case that it is the same. Okay, hold on. Now it messed up. So we fix these. What's wrong here in this case? So let's say, so 10 here gonna be 0, right? Okay. Okay, so this case we should special for the case that it is equal, right? So like if 2n equal to n and length of this greater than 1, right? So that is the case. Or okay, first we gotta do if 2n in frequency, right? Okay, so then it's branched into 2 case. Okay, so first we check that. So for the case that we have the same number here, we want the length, and okay, length, okay, so let's do let's strike out our test case first. Okay, so first if 2n equal to n and length of this greater than 1, then it is the the zero case. So the real zero case, right? So otherwise that means either this is false, right? So otherwise we say if to n in frequency, right? Right? So that would fix that, right? Oh, case V is wrong now, right? Okay, so if 2n is in frequency, and so like case 0, we want it to be greater than 1, right? Otherwise, and okay, so case 3 here is wrong because this is okay. Hold on, let's list out all the, this will become right. So 0 0, right? Right, so this expect false. Negative 2 is 1, 2 is 1, 2, right? So it fell because resin and land is greater than 1, right? So it because still true here, right? So if we do this, we fail the fourth case, the first case, right? Which is let's just list out all the things first. So this case right here must be false. This case right here should be true. So we have 10 0 to 1 5 2 3 4, right? So we want 10. Okay, check it's true because if we check 5 and it found 10, right? Right. So in this case the number of it's fine, it found 10, right? And then it checked the length has to be greater than 1, right? So only the number, okay, if 2n equal to n and length of frequency is greater than, okay, and 2n must be in, and okay, so n for sure in, right? So and length of frequency of n, right? Greater than 1, then also return true, right? Otherwise we just need to check this thing. Right. So let's see, the case we fell because why? We have This one we expect false. Oh, we have that up there. So okay, 0. Okay, 0 in 0, and we return true somehow. So 2 multiplied by 0 is 0 as well, right? So it would not in this case. So then, okay, we have to do n. If 2 equal to n. So in this case, right, we found 0 actually in. Okay. So number 0 is special here. Okay. So this is condition for this. If it is equal, then the length must be. Okay, so first let's tie break on that. So if to n equal to n, right? Otherwise it is not, right? So in this case, if length of the frequency n greater than 1, that means 0 0, then this is true, right? If so, that means if 2 the in frequency, right, and return true as well, right? How is that not different from this? Or maybe we have to do LF here. Try it out. Okay, so actually let's test that theory out. So here we gotta do, instead of do a double if check here, we do LF. No, whatever, let's just do this boolean that we did. So only when this number equal, then it's true, right? Otherwise, if this, how is that not different? I'm so confused. Okay, how that not different from here? Then true, right? Elif. Okay, fine. Let's just go with. Let's put some comment. Is this not equivalent of the above? Right? Run this. Okay. Mid. Okay. So, okay. Time complexity is. What is this? Time. This time complexity is actually ON, right? Oh, what is this, bruh? Why do you not rate limit me? Check if n and it's double exists. Time. O of n. Because you still have to loop through them. Okay. So let's do the GitHub thing. is okay, so this is the one. Check if and it's double third pi. Okay. 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 We write some tests. This is probably something we need to do later, right? It is not. This is array expected. Okay. So the test case here. So we probably need a norm function. Okay. This is from our lead code module import norm. Okay, so Python check if n. Alright, in runtime. Is on, right? Millisecond 47 90 19 32 51 50 and this is okay. Check if Let's commit, amend this. Okay, input. Let's see. All right. Maybe get push. Okay. So that is done. Now we look at. Oh, thank you, Coding Cricket, for follow. Sorry, I didn't see that. But thank you for the follow. And okay, so now we do. Okay. Okay. Okay, so let's look at what is this? This Walmart one. I don't know. I think they don't. They're being very secrecy about stuff. I'll do that later. Gemini. Probably spend some time with Docker later on. Next stream or something like that. But now we look at what is it? Healing. So what is this? We'll look at Kafka at Airbnb. What is this? Robinhood. Okay. So Airbnb. So what is it? 6 years ago. What time is it? 2019. So let's look at. We look at this article first. Okay. Post it here. Post it here. Okay. So first article is scaling Spark streaming. So this is 2018. Then we have a 2019 video here. We can take a look. The progression of Kafka in Airbnb, I guess. This person's still here. Engineering manager. Still here. This is software development engineer though. Doesn't seem like what year is this one? 2019. They have a video on Databricks. What? So did they do all this in Databricks? It's the same Hawang or something. I don't know. Hold on. 2018 they have this. Let's just read them by time, I guess. So 19 we'll look at this. Okay. Get some water. That look like an old trail app instead of Airbnb. I guess. I don't know. Okay. How Airbnb skills Spark streaming with a novel balanced Kafka reader. So every interaction with the app or the web browser, they would file event. So the user interaction with um, so let's just say this is client to Airbnb, right? So user interaction client, so it should be like app or web browser would fire the event, which go to Kafka, right? Or something. Kafka. Okay. Okay, so they basically this event basically analytic, right? Because they do machine learning, right? Near real time. Okay, so from Kafka you go out into some sort of data warehouse. So for them it is Spark, basically Spark, then HBase, and then Hive. Hive is the, I think, the Spark object database, right? Object file, right? Spark Hive. In memory database, in memory, yeah. HDFS, you have a file system, right? So they don't use S3, right? So I think Netflix also have HBase. Right? They also do something, right? Hadoop, do some sort of map reduce so that you can crunch through all this big data, I guess. Okay. Do some sort of machine learning. So what is Airbnb SLA? I don't know. It didn't say. Okay, fine. So basically this area has having a problem right now. So basically this right here, Kafka to whatever this thing is struggling with massive data ingestion. Hmm. What is this number? They're saying it is. What did they say? Didn't say. Oh, the HPay here they dedupe, right? Look like that. Dedupe. Dedupe. Okay. And cooking. So this is what Walmart also find out, right? Consumer can never be more than one partition. Each partition should usually have one consumer. That's what Walmart find out, right? Or whatever. What is this? So right now, I guess the main problem is one partition, Kafka partition to one Spark, right? Is that the problem? Because the partition is getting big and Spark couldn't crunch to them fast enough or something. So I guess then you need to design your partition better, I guess, so that the data going into partition is less, right? I don't know. Yeah, see, this is the problem. So Spark parallelism is not scalable. Seems the process to increase Kafka partition and manual. Okay. So you basically have hard partition because Listen. Concentration die spiking. Very greatly. Yeah. So you basically have big size. So like you have in a partition, it's like a pipeline. If more event come in, but you cannot scale the spark because of the partition, whatever. So my guess is would be that somehow you have to uh, fan out the partition better so that you have evenly distributed the data across different partition, right? So basically what they have is, or they call here skew, right? Event. Okay. So the only way you can do that is to bash them, right? So current situation when this delay is to batch more messages into Spark, right? What is this? Basically increasing or aka batch window increase, right? So somehow you have to display evenly distribute the data across all partition, then it should be fine. Okay. Balance the Spark Kafka reader. Mm. Balance partitioning algorithm. So basically you chunk the partition and you split yourself, right? Instead of having one Spark consumer, you basically give the Spark to read from offset to offset, it seems like. Kafka and 3 split. 2 topic and 3 split. Okay. So the solution is basically uh, stream up. Right, so what do they do here? So basically pre-process the events, split them into chunks, assign to each spark reading the offset, right? Something like that. Okay, so evenly, right? So 1/3, 1/3, 1/3. Right. So depending on use balance partitioning algorithm. You just split them evenly. Sum of the number of events. So each event and their size. So you would just split them by number of fleet. Mm. Mm. Okay. So because you chunk them, right? So each of these can be read from uh by spark. So technically number of split is the number of spark, right? What is that? Yeah. Yeah, I think so. Okay. So basically, lesson advice, understand the data and figure out where is the bottleneck and way to the conscious and with how to say break the bottleneck. Yeah, okay, so and eliminate them. Where are understand your data is important here. Spark has UI to understand job execution, timeout, tune, right? Acknowledgement. Are all these people still here? Gabe Lion or whatever. Airbnb. Data Hub. Will he move on? Data Hub. Senior years. Stay here for 4 years. Now he found an. He become a founder. Nice. What about these people? He went to Amazon. She went to Amazon. Okay, but wait, hold on. Still at B&B now. Why does this stay here? Not up to date. Okay, cool. I guess now we can go to 2019. But let me go to the bathroom real quick and I'll be back. We watch this park here. We watched the 2019, but this is May 9th. This is October, so we wanna watch their big first. But let me go bathroom real quick. Okay. Let me see. Okay, so the main one is, oh, this is the, I guess this is the video of, this is just a video of, this is the video of the blog post. Okay, so we might want to what this? Are they talking about the same thing? Okay. So let's see if we can show it in this one.
All right, thank you, Guozhang. Okay, let's talk about Kafka at Airbnb. Actually, Airbnb is one of the earliest adopters of Kafka. Actually, we started to use Kafka things, Kafka 0.6, maybe 0.7 in production, right? Yeah, and then yeah, we're still evolving, I think. Today we're going to talk about some three topics. The first one is we're going to share some basic Kafka information and deployment at Airbnb. And then we're going to dive into two systems we built at Airbnb. One is called SpellTap. Basically, is our change data capture service we use at Airbnb. We use SpellTap to power a lot of services at Airbnb. And then we're going to talk about the Muscle, which is offline to online data store we use at Airbnb. So, okay, this is our scale. So actually, I think Airbnb has one of the largest Kafka deployments on top of AWS. We're having more than 10 Kafka clusters. We spin up dedicated.
Wait, hold on, let me write it down. Okay. 500 brokers, 3,000 plus topic, petabyte of data, 10 plus cluster AWS. So okay, so they do the AWS.
The services dedicated Kafka cluster for different use cases, and they are on 0.11 right now. Currently, we are also testing the latest version of Kafka in our testing cluster. Hopefully, we can use it maybe next month. Okay. And then we are having over 500 of brokers in total. So most of clusters are using D2 ECS type, and for some high throughput, high fan out clusters, we are using i3. They are having they have SSDs and higher network bandwidth, and we are having more than 3,000 topics. We are handling over petabytes of data per day. This is our high-level architecture. At Airbnb. So we have a lot of applications talking to Kafka clusters directly. They are using Kafka clients, and then we're also having Airbnb use Ruby, and we build our own REST proxy too.
Okay, so basically they have MySQL dash jobs application on the left. They're all going to Kafka, and then basically the map reduce architecture, right? So you spawn stuff and then you collect. So Kafka go to Spark, and I think these two things go to the things, and this Kafka also have consumer. Okay.
To support Ruby and other languages at Airbnb, and we are also supporting offline jobs and batching jobs to send data to Kafka. And then we have we're using Spark Streaming and Apache Flink to send the data from Kafka to data warehouse.
Link.
And then, of course, we have lots of applications consuming data from Kafka clusters directly. Actually, Kafka is one of the most important infrastructure at Airbnb. It supports lots of use cases. And then next, we are going to dive into the Spinotap system. I will hand it to Zofei to talk about Spinotap. You can use this to.
Right, thanks, Xu. My name is Zofei, and I'm working at Airbnb's storage team. So Spinotap is our change data capture system. It's one of the most important system use the Kafka. So then first, let me talk about the motivation why we need the Spinotap as the change data capture system. So as you know, Airbnb is a travel company. If you go to Airbnb's website and let's say you're going to travel to New York, first you're going to search New York, and it'll show you the rooms and experiences on Airbnb. So these search results are powered by our search team. So it is very important to keep the search result up to date. And as you know, the host may update their listings at any time, and maybe one of the listings may be booked at any time. So we don't want to show the outdated result in the search page. That's why we want to keep the search index up to date. And as the source of the events, like let's say the host updated listing is less in the database. So we are thinking that why not we capture these changes in the database level. So when we were designing this system, we came in with this for several requirements. So first, the change data capture system must be lossless. We cannot tolerate any data loss. So in Spinotap, we guarantee at least once delivery. And this right now, almost every system should be scaled horizontally. And we keep adding new databases. The data size, the traffic keeps growing. So it's very important to keep the system horizontally sharding. And so another requirement is this system, the change data capture system, must be performant, because we want to keep the search index up to date at minimum lag. So the system must be low latency and high throughput. And also we must guarantee the order. So in Kafka, we guarantee the order. Kafka guarantees the order of the publish. But in Spinotap, we guarantee the order by the primary key of the database. And also, of course, the system must be fault tolerant and should be highly available. And last feature is we must make sure that this is a general purpose change data capture system. Although we are using Kafka and MySQL in Airbnb, we don't want to tightly coupled with these two systems. We want to build a general purpose one change data capture system, and we can easily extend to other databases or messenger queues. So this is a general workflow of a Spinotap. So we capture the events from data store, and we're using a stream client. In terms of MySQL, we're using open source library called MySQL Binlog Connector. That library will give us all the events of the table level. And then those events are propagated to Spinotap. And finally, Spinotap will convert these events to mutation. And then we publish to Kafka, and then other services who are interested in those mutations.
So some of the database, maybe each row would have to somehow, the data comes in, it had to get out of that database, and then it go to this Spinotap, right? It go to Kafka, okay?
They can just consume those Kafka topics, and then they will get the notification. So as I said, we want to build a general purpose change data capture system. So we built some abstraction layer on top of Spinotap. So source is what we call it. That the first abstraction layer is the source. The source is responsible to capture the changes on the database level. As I said, we use some stream client to read from changelog For example, the MySQL, we have binlog.
So it seems like they have relational database, right? Because if you look at binlog, it would tell you that, okay, what data is insert, what data is updated or whatever, right? You look at that and you figure out, okay, was that add, delete, upsert or whatever, right? You look at this diff and you figure out, okay, keep streaming those data, right?
We got these events and we pass it to the source. And in the source, we do some processing. First, we want to filter out the events as we only care about the insert, delete, updates, those are the mutations from database. And then we have a table filter. Table filter is responsible to filter the tables we don't want. We don't need the mutations. And then last, we have duplicate filters to filter the duplicate events. After that, we pass this event to a couple of mappers. So we map the events into different types of mutations, like insert, delete, update. We have different structures. And also, we need to add the metadata and the table schema. So in this stage, we got the mutations, but getting the mutations is easy, but capturing the schema change is kind of tricky. Because for MySQL case, prior to MySQL 8.0, it's not possible to add table schema information to the binlog. And as you know, SpinalTap processing the binlog, reading from binlog, but there's no table schema version information. So we have to get the table schema information from somewhere. We can query the information schema table to get the table schema, but that's the latest one. We don't know the history. We don't know the previous versions of the table schema. So what we do here is we maintain a schema database. So that's a separate MySQL database. And first, we before SpinalTap connects to the MySQL database, that's our source, we just do a snapshot of all the tables, the table schemas. So we create a bunch of empty tables in this schema database. And after that, whenever we see a DDL in the binlog, we just apply the DDL into our schema database. So at this stage, this schema database will have the same schema. All the tables will have the same schema as MySQL database. And after that, we just read the table schema and we propagate it we save it to a schema store. So SpinalTap will always query the schema store to get the schema of current offset, binlog offset. So this is how we handle the schema evolution. So destination is another abstraction layer of SpinalTap. So we got the source. From source we get the mutations. So now it's time to publish into the Kafka. And in Airbnb, we use Thrift as the Kafka schema, message schema. So we have to convert it to our standardized Thrift mutations format. And also destination is responsible to get the last mutation we published successfully published to Kafka. So now we know like till which binlog offset we have published successfully to Kafka. And we did some optimization of destination. So instead of we directly publish to Kafka, we use the producer consumer pattern, and we use a bounded blocking queue. So we have a thread which takes the mutation from the source, but then we put the mutation into the queue. So we have another thread which takes the mutation out of the queue and then publish to the Kafka. So in this way, we can maintain a low latency, and we also can further optimize it because we only guarantee the order by the primary key. So before we put the mutation into several buffers, several queues, we have a key provider which will do the hashing and then just guarantee the same the same primary key will be in the same queue. So in this way, we can have multiple threads of Kafka producers and further improve the throughput. So we have, just as I mentioned, we have source and destination that will constitute a pipe. We call it pipe. So pipe is another abstraction. Pipe includes the source and destination. So what does pipe do here? Pipe is responsible for opening the source and destination, also close whenever there's a, let's say that whenever there's a Kafka issue, we cannot produce to Kafka. So the pipe will, the destination will notify the pipe, okay, I'm not able to produce to Kafka, and then pipe will just close the source, so make sure we're not consuming from the source anymore. And also the pipe is responsible for checkpointing. So we have to keep checkpointing where we are, how far we have consumed from the MySQL bean log. So it will just periodically do checkpointing to the zookeeper. So next time when the pipe comes up again, to read the last checkpoint from zookeeper, so we know where to consume from the last checkpoint. So the pipe is the minimum parallelism unit in Spinal Tap. So each pipe corresponds to a database, actually. So we have multiple databases, so we have multiple pipes, and that's why we need a pipe manager. The pipe manager will manage the pipes. It's easy to configure. Whenever we add a new database to Spinal Tap, the pipe manager will create a new pipe, or we will delete the deleted pipe. So now it's time to talk about the scalability. And we are using a framework called Apache Helix. So it is a cluster management framework which will handle the failover and the resource management. So in Helix, there's a concept called resource. So we just map each Spinal Tap source or pipe into a Helix resource. So whenever we add a new pipe, add a new source to Spinal Tap, we just essentially adding a new Helix resource, and the cluster manager will just create that resource in Helix and will assign a leader for that resource. So in this way, we can achieve the high availability, and we are using the leader standby mode, and there's always a leader which is processing, running the Spinal Tap pipe, and if that leader is down, and Helix will handle the failover, either elect a new leader for this source. So we're also using a consumer-side write fencing. So let me explain a little bit about this. So each Spinal Tap pipe will have a leader epoch. So initially it will be 0 or 1, I don't remember. So once there's a failover by the Helix, we just increment this leader epoch. So the new leader will have a different leader epoch. So in this way, the client side, when they see a new leader epoch, okay, so the client will know, okay, there's a failover happen, so we should not consume, continue to consume the older epoch. So in this way, in case there are multiple leaders, leaders producing to Spinal Tap, from client side, we can filter them out. So these are the guarantees, Spinal Tap. And like I said, we only guarantee, at least once delivery, and the event ordering is by primary key. And right now we support MySQL and DynamoDB as a source, and we support Kafka, of course, and also Kinesis as the destination. And this is let's talk about the use case of Spinal Tap being Airbnb. This is a very classic one, is the cache invalidation. So the service writes data to database, and also there's another service called cache invalidation. We'll just listen to Spinal Tap, and whenever it reads the update or delete event, it will just invalidate, send an invalidation request to the cache. So the cache will be invalidated asynchronously. Another use case is
So basically, they access the data through Spinotop instead of directly the database, eh? So basically, this is like a data hub, right? And then because they control that, they can just invalidate the cache if the data is updated or whatever, right?
like I said, the search indexing. So the search indexing, there's a search indexing service which listens to Spinotap and then gather the necessary information from other services maybe, and then just update the index document. We use, I think Airbnb, we use some services they use Elasticsearch and some are using Lucene. So the last part is the validation. So how do we validate? How do we make sure the Spinotap published to Kafka all the mutations, all the table mutations correctly? So in MySQL case, because we have bin log files, so we create a validation service which will continuously download the bin log files from MySQL, and then that validation service also consume from the topics, the Kafka topics Spinotap published to. So after they get all the mutations for that bin log file, it'll start validation. It'll just compare all the mutations it receives from the Kafka and the bin log, all the events from the bin log file. And last is Spinotap core part is open source, and we also have a blog explaining how Spinotap was designed and implemented. So if you're interested, you can just Google search like Airbnb Spinotap. And I will hand over to Chen Chen. He will talk about the muscle or key value store.
Cool, thanks, Sophie. So, hi guys, I'm Chen Chen. I'm gonna talk about the muscle. It's our offline to online key value store at Airbnb that we use to support a lot of the data-driven product. So the first question is why we need this key value store? Because I think everybody knows that in the industry we have a lot of the key value stores. Like why we need to build it by ourselves. So there are a bunch of the tenants that we need to think about. The major thing is about the bulk loading, that we want to make it really reliable without side effect, and also it should be integrated with our internal data warehouse pretty smoothly. And for the performance, we want to get the low latency and a high throughput. So how high is for the throughput? So far, for the single cluster that we support the million QPS level traffic for the read, and for the write, it's around the 500K QPS per single cluster. And by the way, we have like several clusters in a different magnitude. And in order, this is where we want to leverage the Kafka to get it like in ordering guarantees whenever there is a lot of mutation events come in to our storage. I will illustrate the architecture in the next slide. The lossless is for the at least once delivery. For the details and why we need that, I will also mention that later. Eventual consistency is something that we trade off for. For our cases, for Airbnb, we have two kinds of systems. One is an online storage system. Another system, I wouldn't just mention a lot. For this case, this is a derived data storage engine. Like you have a lot of data that you stored in your data warehouse, or like you at least have some backup in your data warehouse, no matter if it's a Hive or if an EMR, whatever. But you at least have a source of truth, not just in your storage engine directly, but it's in your offline data warehouse. So in this case, our products can tolerate some different level of the mutation lags, so that we can use this mutation events via the Kafka and then to populate the data. And all the products can tolerate the eventual consistency. And scalable, this is definitely something that we want, and fault tolerant for the different replication set and highly available. So this is a muscle architecture. So I think one thing I want to mention is for our exploration about some of the key value store in the industry, like the Cassandra and HBase and also RocksDB. So
Cassandra.
there some of the major concerns is like for the Cassandra and RocksDB that we did a lot of the homework and some load tests. And what we found is like for the bulk loading that either of them not supporting pretty well with our internal offline data warehouse. That is kind of a major reason that we want to build that by ourselves that I will mention for the architecture later. Another thing is for the expertise. I think if you just want to build something very fancy and using those technology, I think that is totally doable. But for the company-wise, that we want to leverage the most expertise that we have, which is the HBase back to the 3 years ago, that a lot of our engineers in the infrastructure team are very good at the HBase and its ecosystems. So that's why we want to choose the internal data structure from HBase, which is called the H region, as our key value store. But we also explored the RocksDB, which is written in C++, and it had we don't have a lot of expertise on RocksDB deployed on the production in Airbnb. So that's why we have some. We just hold off a little bit, but we know that RocksDB could have some better read and write throughput and latency compared with the H region. So that is something that we can explore next year. For the architecture, there are several major components that it's worth mentioning about. First thing is the Muscle Dispatcher, which is the kind of like a gateway and to consolidate all the requests, no matter if it's a read and write. And then it'll have some built-in features like the back pressure and also the quota management to guard against all the storage node. So in case this database storage engine wouldn't be flushed a lot. And then for the write events or like a mutation sequence, we will just write to the Kafka. Basically for Muscle, we use Kafka as the distributed bin log. If you have a lot of knowledge about how MySQL cluster works between the master and replica, this is a pretty similar. The concept of
Hold on, let me write down. So dispatcher would read from Muscle store, and basically the dispatcher is controlled by Zookeeper. That's the cluster, if I'm not wrong. That's the cluster manager. So also managed by this. Also store. Cluster control. Oh, so store is the cluster. Also cluster controller. Also managed by these. Okay, so the thing that we need to care about is basically the dispatcher. Go to Kafka for the write. Kafka also talk to Muscle store. So everybody go to Muscle store. Okay, so the store is also back up to S3. Okay, so this is right. Right. So this is read. Okay.
Pretty similar. Like we use a Kafka to as the bin log. So for all the muscle storage nodes, they can consume from those Kafka, and to given this ordering guarantees, then for each partition, then each shard in the storage node can just consume the data from the Kafka and try to apply to the appropriate tables and partitions well. And then there's a cluster controller. This is something that we leverage by the Helix. I think Zofei also mentioned a little bit about that part. It gives us a lot of the, like the benefits instead of building some Zookeeper clients just on top of Zookeeper. So that's how we leverage the state transition and also some state management in the cluster controller for how to map the dispatcher to the instances in the storage nodes. For the client side, basically, there's an online client, like client service, and an offline data warehouse. The major thing is for the offline. I will try to mention about it later. But here, the principle is whenever given the offline data, we can first generate the H files, which is the format used by the H region. For the RocksDB, you can use the SS table. But I mean, the idea is the same. Use the SLM data structure to format this file. And then we will just upload this H files into the S3 for the backup. After that, we will just send out some load events through the dispatcher and via the Kafka to the storage node finally. Then storage node will be notified to say, this is the time I need to download the H files from S3 into the node. And for the after the download is finished, the switch is atomic operations that you will directly either override or like a merge the data together. So basically, for the sharding part, for the bulk load, what we do is a MapReduce job that we just build using the cascading Apache cascading framework to do that. And here the point is like you should control your shard numbers, because this is a critical when we use the use a Kafka and we set up a fixed set of the partitions. How you can just map your shards into the Kafka partitions, and also for each storage node, it will need to know which partition it needs to consume from. So given this diagram, that I think the idea is very simple. It's like given each reducer, after we generate the H file, then we upload it into the S3, and then for each dispatcher, when we receive the load file event, produce that event into the Kafka, and for the storage node to consume that event, and based on the information fetched from the cluster controller, and then you will know for each partition what kind of the Kafka partition that you need to consume from. For the sharding for the real-time mutations, this is using the same sharding algorithm with the bulk loading that I mentioned on the last slide. But actually, for this real-time write, then you will directly write to the dispatcher gateway. And for that gateway, we will know, okay, for each mutation event, you will know which partition that you need to send to. I mean, the partition is the Kafka partition. You will know which one to send to. And then the similar way that a storage node will know which partition, Kafka partition that it needs to consume from. The query data, very, very similarly. So we use the exactly same sharding algorithm for each read request, and to read from the dispatcher. But here we don't need to rely on any Kafka, because let's say if you have a master and a slave, then you only use the Kafka as the bin logs, right? So that means that only applies to the write cases, not for the read. And for the performance issues, for each dispatcher, it will try to regroup the order request, because each request is a batch request that we support. And you could just regroup them into different, group by the Kafka partitions. and also for the storage, for the Kafka partitions. And then you will send a batch request to the storage node, and you will fetch the data as a batch request, and then aggregate them at the dispatcher level, and then return. And this is the partition rebalancing, which is pretty common in all the key value storage. But for our cases, because we use the Kafka, so there is a little bit some subtle differences here. It's like for Muscle, we designed the two different modes interchangeably. So each instance could be either the batch mode or the online mode. The difference is like for each batch, if the instance is in batch mode, that means this instance doesn't serve the read traffic, but only does the daily backup, just for the persistence and also for the major compaction. I think if anyone have a heavily rely on the HBase, maybe you will know, like if you want to do some major compaction to improve your performance, there needs some dedicated care about it, how the major compaction wouldn't affect your read performance for your cluster. So usually we do that on, let's say, in the midnight for that part. But for our cases, because the batch mode doesn't support the read traffic, so that means, and also for the write traffic, you have the eventual consistency depending on the Kafka. We just need to guarantee some eventual consistency. So it is fine that we can do the major compaction to improve the performance of the batch mode instance. And then for each day that we will switch the nodes between the batch and online mode. So that means the batch mode nodes for the next day is going to be the online nodes, and all the H files has been compacted. So you will just get the less H files and then to get a better read performance. And for the current online nodes, for the next day it's going to become a batch mode nodes. So you can do some major compaction without affecting any read performance. How we do that is it's quite simple at this moment. It's like you can just create a nodes, and which is the 2x of the batch mode nodes. Then we will put new nodes in the batch mode and do some provisioning there. There are two things that we need to do. First thing is we need to have all the daily snapshot to be downloaded. So you will have like a baseline, right? And then for the Kafka mutations, because we record the offset in our logs, and by consuming those offset, and you will need to catch up with the Kafka mutations until up to date. And after that, we will say the batch mode nodes is a consistent, or like is up to date with the other nodes. So then you can delete the old groups and repeat for the next groups. For each group here, what I mean is like for the replication set. Basically, we will have a lot of a replication set, so that you can do that. You can do each group at a time, and for many times. We also just automated that part. Partition resharding is another interesting topic, which is so why do we need a partition resharding? If you think about a Kafka, it's like if there's a hotspotting, that for the rebalancing, it's still not enough to make sure that your single shard can support the, let's say, very spike read traffics, like for example, like the email scheduling or like the search cases at Airbnb. So we will need to do that partition resharding. Generally, this is happen very rarely at our scale, and also maybe it's pretty lucky that thanks to the well-defined schemas, so we didn't just encounter with this problem a lot. Yeah, and this one is feasible, but it's expensive because of the heavy operations. Given our architecture, you have to take care of the storage node and Kafka, and also for the MapReduce job. So how do we do that? If we must do that, so here I just give an example. It's like, let's say we currently have like a shard 0 to 7. You have 8 shards, and now you want to just double it to, let's say, the 16 shards. So then what we do is we will first have like a shard 8, and then you will have a do write both the batch and the streaming write events into the both the shard0 and shard8 through the dispatcher. So at this moment, we can make sure the shard0 and shard8 has the exactly the same data, right? And for the step B, the dispatcher will try to redirect the read and write shard8 data from the shard8 only, because in this case, shard8 already has all the data. But note that we have another one is the batch job, which is the set of the different shard there. So for this case, the dispatcher will still routes the same load file request to both the shard0 and shard8, so that both the shard0 and shard8 can just load the data correctly for the for the bulk loading. The step C is the double the H file reducer that we mentioned, because the reducer, the number of reducer controls how many H files we will generate it and upload it to the S3. From there, and using the same sharding algorithm to map the data, map the shard8 data into the shard8 H file. So then you will have a double your H files in the end. And the step D, so eventually the dispatcher can, okay, and this moment we're safe to make sure the dispatcher can route the shard8 load file request into the shard8 only. So shard0 doesn't need to maintain any data from the, which is supposed to belong to the shard8, depending on the splitting. So here I would like to just give a brief talk about some use cases, real active use cases at Airbnb. One is a user profiler, which is used for the search team. For any guest comes into the Airbnb, we will try to just track your history and your like your navigation through the different pages and events. So this is a user profiler. What's the architecture is like for each application, or like in your pages, or like a user behaviors? We will just try to emit the events into the Kafka, and then the Kafka internally will have two streams. One is the direct stream to the Flink. Another one is a stream to the data warehouse. And for each day, the data warehouse team will just generate the daily snapshot for that Kafka events. And then for the Flink, so our user provider team provides the two things. One is using the Flink streaming programming mode, and to just ingest the data directly from the Kafka and load them and do some transformation. It's kind of like an ETL, and then write to the Kafka directly. Another way is they use the Flink, the batch mode, to read the data from the data warehouse, and then they just generate the batch H files, which is a little bit different than what we do for the MapReduce. And then they just put that in the muscle. But here, they just create a separate muscle tables. For example, let's say you can have a user profiler real-time table, and you can have another real user profiler batch table. And so there are two tables stored in the muscle. And for the online serving side, for the user profiler service, they will just try to read and aggregate the data on the application side. One example is for each user, you will have a different events, right? For events, you just flush into the LSM file, like the H files. And when you read them, you can just given the range of the timestamp, then you can just fetch multiple versions of one users. Given if you define the each version is each event of this users, and then you can do whatever aggregation that you want in the application side. Another case, which is also similar architecture, but it's interesting part is for the machine learning feature engineering platforms, what they are doing. So what they are doing is they have a feature set declaration API, and they use to allow any client teams to do some configuration and to set up to say, hey, I want to create another different feature set. And after that, they have a pipeline to automatically build up the feature set streaming, which uses the Flink as the underlying parallel computing platform. And another case is using the feature set batch, which uses the Spark for their batch uploading. And then both of them will just try either stream or either batch load into the muscle, given the approaches that I mentioned before. But that team, they also created separate muscle tables in muscle, so that in their feature fetchers, they can just do either multi-version aggregation or like a multi-version some counting or like a different aggregation approaches. They can do that there. And the application, and that layer is abstracted so that all the applications, like what we have is for the trust cases, if you want to do some fraud detection, they don't know what's the underlying storage engine. They only know there is a feature fetcher that they can use to directly fetch the data from the underlying data storage, but they don't know what kind of a storage it is. So that's how we try to abstract it as much as possible for between the client team and for the machine learning infra team and our storage team. So that is two use cases that we have. Yeah, I think that's all the things that we want to mention. And if anyone has any questions?
Any questions?
Do you want to come together?
Okay. Let me ask one question about the first system that you guys have been built for schema evaluation. So it seems like you are basically trying to capture any schema changes in real time and basically do the schema changes in your store immediately. Does that actually rely on your bin log to be totally ordered and you only have a single reader from the bin log?
Yes. We do have a single reader for the bin log.
And how actually impact your performance? Because if you have a single log and your bin log is expanding rapidly, and in order to really capture the schema changes along with data pushes as well, you have to basically follow this order.
Are you asking like the single thread bin log reader will affect the performance?
Yeah.
Right now, I think our QPS is okay, and we haven't seen like very significant issue of like single bin log reader, because I think for the client, for the MySQL bin log connector, that client is just to try to mimic the behavior of a MySQL replica. So that's why keeping it as a single thread will make things easy, and we don't have to worry about the multi-thread contentions. So for now, we just keep using this client that by default is like single thread.
Okay,
Yeah.
Thank you. Cool. Let's thank our MBMB folks again. And that wraps up our last talk. And again, a final note that the next month, we're going to have our 4th Kafka meetup in our Mountain View office. So, and we'll have new talks and also from other folks from potentially Dropbox and Netflix. So stay tuned and welcome to join our next meetup as well. Thank you.
Okay. So I think that concludes this session. Probably come back tomorrow because probably now I'm probably play some games and then sleep. All right, see ya.